first just to introduce myself a little bit. I'm Jeremy Rubin. I am, I guess, the founder of this expo. Like many, many years ago, in 2014, we had the first one, just a few buildings away. And it's really great to see that it is still going on and in such good shape. And I wanted to say, before I get into my own content, that I'm really happy about the Freedom Tech theme this year. A couple years ago, yeah, exactly, round of applause for the organizers. I was going to have to prompt you to do that, and then you guys all did that for yourself. It's really great. A few years ago when I was here, I looked at the agenda of who else was talking. I was like, oh, I probably just need to do a talk about why we're even here in the first place, because it was all sorts of, we could build this or build that. And it's like, well, it's all about freedom technology, and seeing the expo get back to those roots is just, it's really phenomenal and really great work from the team running the expo this year. So that said, what is the Char Network? I think I've been building on it for a little. People always ask me, what is the Char Network? And I always respond tongue-in-cheek. I'm excited to find out as well. Char is a system to deploy and run decentralized applications and layer 2s on Bitcoin. It is a network of staked bonds that allows you to sequence applications. We've heard a little bit about rollups and sequencing, so it's solving that problem. It allows for multiple bonders that you can reconcile a various sequence of messages, makes it expensive to cheat. It's auditable. It's a set of SDKs to build those applications, and a system of incentives to guarantee that it's secure. A lot of that is still work in progress, and this is a talk maybe a little bit aspirationally about how the system is coming together. So because we're focused here on freedom technology, I wanted to talk about maybe a single application. So it's not the entire Char network, but this is something that you could build on top of Char, is a decentralized mining pool. So why do we care about decentralized mining? Well, the sponsor, the lead sponsor of this event is the Human Rights Foundation. So I thought, why not take the word from, directly from the horse's mouth? Centralization in Bitcoin mining threatens its censorship resistance. So if we want Bitcoin to be censorship resistant, we better decentralize mining. And if you look at the actual distribution of hash rate and you do a little bit of snooping, what you'll see is it seems like mining just from a first glance is centralized, but if you look a little deeper, it's actually even more centralized than you might think. It seems like a lot of the pools that seem to be in different entities may actually be running identical software with identical databases. Maybe that means that it's actually all just one company under the hood running all of Bitcoin mining infrastructure. That's not really good. Maybe we can build an alternative. So before we get into how the alternative gets built, let me introduce some of the core concepts behind the Char network. And the basic thing is an attestation chain bonding protocol. So what is an attestation chain? The core of that is just a linked sequence of signed messages. So you sign a new message, and that new message commits to all the previous messages that you've ever had. So you get a nice linearization. It's basically a blockchain, but instead of proof of work, you have a signature. So one person could maybe forge a message. So how do we know if we see two conflicting statements in our chain of messages, which one is the real one? And the answer is we can't really know. But what we can do is if we detect two conflicting statements, we can extract the secret key that was used for that chain. And we can basically build, on top of extracting a secret key, a smart contract gadget that, with the knowledge of that secret key, allows the bonded oracle's funds to be burned. So what this lets you do is it lets you launch as an oracle your own little blockchain. And instead of having a baked-in reward to build the chain, you have a punishment if you don't build the chain in the honest way. And now we can kind of be sure if we see one of these chains, yeah, there might be another one floating around, but if you ever learned that other one, you'd be able to inflict a heavy penalty onto the provider of that sequencing. Inside of each of those sequences, it's not just a chain of signatures, you also have some data that's committed to. And then you get a linked sequence of data that you can reference. And in Char, the way that we architect that data is as a sparse Merkle tree. A sparse Merkle tree is, Bitcoin has a Merkle tree of transactions in every block. It lets you look up and see, is there a transaction, at any given point without necessarily looking at the whole block. Sparse Merkle trees are a little bit different because they also allow you to give an exclusion proof. You can look up and see if, for a given key, there's no data present, which is a nice and useful property. The way they work, a little bit out of scope for this talk, but you can think of it as just like a regular hash map that you can check if an entity is there, you can retrieve it, or you can check and see that there's nothing there. So with that, we then use our special hash map with a key that is the hash of some piece of code that makes up our smart contract logic, and a value that's some argument that we want to call with that function. And each of those functions that we have should have kind of two pieces of an API. At core, you'd have some sort of process update that takes a piece of call data and runs it over the function. And then we have some reading function that says, well, given that we have a state of our application, can we query for, let's say that you had a DNS application, as we just heard about, you would say, like, given this name, which Tor hidden service should we actually go and visit? That's an example of reading data once it's been updated. And so our sparse Merkle tree ends up looking like this. Instead of having keys that are arbitrary, you look up by program X, and then you find the call data that's associated with program X. Stitching that, I guess I'll just show this is kind of in these visuals how we'll show an exclusion proof or how we'll show an inclusion proof. You can keep in mind that there's a sparse Merkle tree there, but we can filter, because you can do this exclusion proof, to look up the data for a single key, which is a nice scalable property if you don't care about all the data. So now we have our sequence of messages that are signed, and we filter by application. So we're just looking at program X, some general program, and we get a list of data that's relevant for that channel. And we can take that list of call datas. Actually, this slide maybe should be a little bit later, but throughout all of this, I'll just say before we go further, we're going to make a simplifying assumption. You can use multiple bonds. So you can have multiple sequencers, and you can reconcile them into a single linearization or serialization of all of the history. It's a little bit more complicated to do that. So for this presentation, we're just going to focus on imagining there's one single bonded oracle that everyone's using. But keep it in the back of your head that they're, in a real world system, you'll use multiple, and you'll find a way to coalesce them into one view of consensus at a user application level. So we take those program call datas, and we call our process update function on them sequentially. So this is basically a replicated state machine, and we're doing a functional fold over all the call data. So we keep calling this process update function, and we take the result of that with the first call data, and we run it with the second, and we run it with the third as sort of like an accumulator. And we do this not just a couple times, we do this every single time there's a new piece of data. And in between, every time we call it, there's an opportunity to read some piece of data. And where is this call data coming from? Like, is it just random? Well, maybe you read something that's interesting to you. You see, oh, there's actually something that I could respond to, and then you yourself would write a piece of call data that then goes into the next update. It's a generic kind of smart contracting paradigm. So now that we have those basics on the Char architecture, let's look at what it would look like to put in a program that's specifically a decentralized mining pool. So the basic API that we would need is to be able to ask the contract for a block template. We'd say, hey, we are wanting to mine these new transactions. Please tell us what the block template should look like in order for the contract to recognize this as a valid block. And you would call this get block. That's a readable API. And you'd want a write whenever you find a share. So in a Bitcoin mining pool, I'm sure many of you are familiar with how that works, but you have an idea of blocks that are valid blocks, which can go directly to the blockchain, and blocks that they've done some amount of work, but it's not enough. And you can use them to show how much hash rate you have, what your participation share is in the pool. So you can submit those fractional shares as well. And the pool will keep that replicated state machine and keep track of how much hash rate each person is contributing to the pool. And you could also request a payout. You could say, okay, I'm done participating in the pool. Please pay me out in the next sequence of blocks. So that's all a little bit abstract. So let's kind of map this out visually. So here we have a sequencer. We have some initial state of, this has been running for some time. And we're going to query, and we're going to ask all of our miners are going to ask for a block template to start mining on, and then they're all going to start doing their thing. The data at this point in time, let's just say randomly, miner A has 20 shares, miner B has 5 shares, and miner C has 10 shares. That's the data that the contract is storing. And then miner A might find a block. When miner A finds a block, they're going to send that to the sequencer. The sequencer is then going to form a new commitment. They're going to form that new root, and that root is going to contain the call data for that program X. And one thing to keep in mind is we're showing a single application. That root is for a sparse Merkle tree, and there can be many applications happening simultaneously in this bond, but we're just looking at a single application running inside of there. So then after a block is found, everyone will call to get a new block template. They want the new data. They want to know what the new set of payouts should look like. And then they'll continue processing. This is what the data would look like. There's not been any shares found since that block was found. Then maybe there's some other update that happens in the system. And so you'll see no data committed to, but there's some other commitment for some other applications. You're ignoring that. Then miner C finds a share. And they say, hey, I found a partial work share. They send that to the sequencer. The sequencer then creates a new commitment. That new commitment contains the work share that miner C found. And everybody queries for what the latest block template is. This type of design can be made resilient. You don't necessarily need to be working on the latest template for it to still work, but you generally would be processing on whatever the latest template is for the pool. Our updated table at this point, when you call for that template, looks like A has 0 shares, B has 0 shares, and C has 1 share. And you just keep processing. Some other data comes up. It's not really relevant for you. You ignore it. Then B finds a share. B submits the share to the sequencer. The sequencer sequences the message, includes it. And then this is what our state looks like. I'll stop showing all of the some of the extra data around getting templates and stuff like that. It's just happening in the background. Keep that in mind. C has 1 share, B has 1 share, and then miner C finds a block. So C submits that block. Now that block is based on the block template that was suggested by the pool. The call data, when it's processed by our process data function, is going to check that block template was a valid find if it's going to be included in the pool, and then update the tables accordingly. And those blocks can directly pay out to the miners that have requested their payouts. Okay, so this whole design, I put this slide in there just for the benefit of, I think sometimes people like to play a game when I'm talking about something, which is find the covenant. And there's no covenants. It's a separate design. I do other things. They would help. Those payouts that we're doing to miners, if they were done inside of a payment protocol like Arc, would be much more scalable and private, efficient. So that would decrease the size of miner that would be economic to participate in the pool, and decrease the amount of custodial risk that you bear as a miner using this pool. So that would be really great to have Arc. It turns out, even though there's a version of Arc that works without covenants, if you want to use them in a mining pool, you really need this non-interactive form of Arc, because every time you make a template, you can't really interact with all the miners to get a signature from them. So we need a non-interactive Arc. The bonding protocol for Char, it does not use covenants at all. It doesn't use covenant emulation. There are different ways of structuring some of these bonding proof-of-stake contracts that don't require covenants. The overall game theory for something like this is that if you didn't have the bonding, then you're relying on a centralized pool operator, and the pool operator can lie to you about what the payoff should be, lie to you about how much work is done. This, you're logging publicly what all the work shares are, so everybody can audit. Everybody has the same picture, and if there's any equivocation over that, then the pool operator can be punished, or the sequencers can be punished. So there's not going to be equivocation, especially in this design. If the bonded collateral exceeds 1 block reward, there's no incentive to be able to cheat. And then in terms of censoring, you might wonder, well, what if I find a work share and then it isn't getting sequenced? You can also provide a tip to the bond operators, and the tip to the bond operators guarantees that they have incentive to include your message, kind of like a transaction fee. So now I'll loop back kind of to the very beginning of this. What is the Char network? It's a system to deploy and run decentralized applications in layer 2s. So whatever you're interested in building, this is a new primitive that we're building into Bitcoin Core. So it'll be right alongside, and you can use this for coordinating all sorts of different applications. And you'll have an SDK and sort of way of incentivizing participation in these that will allow you to launch all sorts of new things. And there's a lot of research that we're doing to make it even more efficient. Some stuff with zero knowledge proofs that let you kind of compact how that replicated state machine runs. A lot of good research directions there. Just examples of other applications that can benefit from being able to use this sequencing primitive. Rollups and sidechains, BitVM, those are kind of the obvious ones. You hear them talk all the time about how they're going to solve their sequencing problems. But it also works really well for things that are just as simple as a multi-sig wallet. If you have a multi-sig and you're trying to coordinate with a couple friends around how you should spend money, you all kind of need to agree on which PSBT you're going to sign. And this is a way that you could use this as a broadcast channel to be able to say, are we all on the same page? And are we dealing with the same underlying data set? It can be useful for all sorts of service providers like ASPs. If you're signing off on your partial PSBTs, your peers might want to know that there's no other version floating out there. This is a way of making sure that that data is deduplicated and consistent, as well as things like routing tables or name services. There's a lot of useful applications for this new data, and it's also not data that has to live inside of Bitcoin. So the sort of core ask that I have right now is we are hiring. So if this is stuff that's exciting for you, we have an in-person office in Miami, and we're hiring for people who want to do like low-level systems engineering, Bitcoin Core, C++, Rust development. Just reach out and let us know, and we're really excited about what we can build to empower the next layer of freedom technology for Bitcoin. I think I've got good time for questions if people want to ask anything.
Hi, Jeremy.
Hey.
So it was a couple things that weren't clear. Where is contract data kept?
Like where is the contract data being kept?
Yeah.
So depending on the application, the contract data doesn't need to be like the contract code or contract data.
The state.
The stake or the
state.
State. Okay. So for the state, there's the call data, which is like the arguments, and then there's the state that's generated. You really only need to store the call data, and there are ways of compacting that. Because of our sparse Merkle tree structure for applications you don't particularly care about, you can prune that out. If you're running a node, it would be stored on your node in like a database, but it's not consensus required. For a given application, you can just rerun the the validation. It's like kind of client-side validation style. Does that answer your question? Or
I think that does. Do you need to store everybody's state or just yours?
So if you're like a full node, you would want to store as much data as possible. But because of the the sparse Merkle tree format, you really only need to store for applications that you're interested in.
What would incentivize a full node runner?
So something that like just in terms of like any incentive whatsoever. So for something like a mining pool, you can incentivize sequencing by like demarcating that in your work share, you're paying an amount to the like set of like stakers. And then there are other ways also of like longer term incentivizing like this sort of network as well. It's hard to do it like fully like Bitcoin denominated. So sometimes there has to be potentially other incentive mechanisms, but there are a lot of applications that can just be pure Bitcoin denominated.
It might make sense to integrate like full node or at least stake like hosting with the mining pool capability to kind of like couple those incentives.
Yeah, absolutely.
And also the other question I have is, okay, so now you have smart contracts. Where do you keep the sats? Like where are those?
So the mining pool is a particularly interesting application because you have the sats wrapped up in a future block to be mined. It's actually non-custodial, and so when at the point of mining, you just have to send in order for it to be recognized into the address that's been told to you as the block template coming out of the contract. So it's a fully non-custodial type of setup. If you wanted a custodial setup, you could also say it goes to this address, and then that address would be like a multi-sig or something. That multi-sig could also be coordinated by Char, but then it would be multi-sig custodial. For the mining pool itself, it's fully non-custodial though.
So it always boils down to a DAO is essentially a multi-sig.
Yeah, and for like rollups, a lot of them have like a big federation set, but they still need like a sequencing layer to decide their consensus. Even if it's a big federation, they might not be able to agree on which transaction they're doing.
Very clever stuff. Thank you, Jeremy.
Yeah, of course.
Is there a paper for the implementation of the bonding for the multi-party for the sequencers?
There is a paper. We haven't published it. And there's like an implementation, which we're, sort of getting production grade before we publish.
Okay. And then also, as far as the bonding, is there in like interactivity, like is there like variability? Can you slash part of it, or is it more like a cryptographic, like reflexive kind of thing that you mess up somewhere in the state machine and that breaks the crypto, or how is that?
So basically, the right now, the only way that you get punished is by equivocating. So general, like if you just committed to garbage data, it should be ignored in the client-side validation model. There are ways of guaranteeing that you commit to valid data under the keys, like is data valid function. But those are not a current part of the design. It's sort of related to future work around like fraud proofs.
Okay, and when's that paper come out, and where can we find it?
That's a good question. Hopefully soon. We're aiming to put out a lot more by May, but it is a little bit early preview.
Hi, Jeremy. So I did Harvard CS on MIT CS, so some of this was over my head. But I was curious if you could explain the value proposition again in really simple terms.
If you're working on any sort of protocol on top of Bitcoin, you need some way to share data with your peers. And if you have peers who are not particularly trustworthy, it can be extraordinarily difficult to make sure that you all have the same data. This is a way of getting data that can be sort of consensus guaranteed against a Bitcoin collateral that if you got incorrect records would be slashable. And so you can basically say if you have an application that's running, it's incentivized that those are the records that everyone has. And if those records get falsified, you get a public signal of Bitcoin getting stolen from those bonds. So you would see that there's kind of an attack on the network.
So this is a collaboration tool, fundamentally.
Yeah, fundamentally a collaboration tool in a way of building scaling solutions for Bitcoin.
Hey, this looks pretty cool. I'm curious exactly what functionality you need to implement that like touches the internals of Bitcoin Core compared to like using the existing Rust ecosystem, or like what pieces are missing that you're probably not going to build because you're busy building this instead of like tooling. But like what tooling, like Rust tooling, is missing for what you want to do?
So I think that one thing that is missing, and I know that there's some work on it for like IPC interfaces with a node, but we really want this system to run in perfect lockstep with Bitcoin consensus. And so because we want that, we implement inside of Bitcoin Core the C validation interface. And every time a block is mined or submitted across the network, we are able to like read that signal and react to it. It's not real-time software, but basically real-time. And most of the other interfaces, you end up implementing like kind of like a long polling based solution. And then also in terms of like writing the Bitcoin transactions that we're doing, they are standard, so they're relayable. There's no problem with that. But a lot of the tooling is not like quite there for, at least in my opinion, for building things that are a little bit outside of the like commonly used patterns. So we're doing some stuff that's not, maybe a little bit more bleeding edge. So that's why we're building inside of Core. In terms of how we're actually built, one other notable thing is we use Bitcoin's peer-to-peer layer for broadcasting the messages for attestations, not in a way that if you're not participating, it would have any impact on you, but that is able to then sort of inherit some of Bitcoin's network properties, which I think is also nice. So those are some of the reasons why we're not just building a completely separate system.
Thanks.
Awesome. Thank you, Jeremy.
Great. Thank you, everyone.